everyone. My YSP project focuses on the design of a planetary habitat for human stays on the moon. Well, rather than looking at the habitat as just a collection of buildings, I approach this as an integrated system, one that can support human survival, scientific research, and resource processing. So today I'll take you through the main ideas behind my lunar habitat and how these different systems came together. Over the course of the project, I explored different systems that would make it possible, from the habitat architecture to robotic assistance to food production, healthcare, transportation, and even how the crew would react with each other. And the first question that I'd like us to ponder about is what a lunar habitat is. So a lunar habitat is essentially an infrastructure which is designed to allow human beings remain on the moon for long periods of time, instead of relying on temporary landers or short missions to the moon. And beyond simply providing shelter, it becomes a platform for scientific research, resource processing, and eventually deeper space exploration. And what should a lunar habitat provide? Before designing the individual modules, I first considered the basic requirements for a lunar habitat. The habitat needs to protect the crew from radiation and the harsh lunar environment. It needs to be a closed-loop life support system with food production, healthcare, mobility, and scientific capability. Most importantly, I wanted the architecture to be modular and expandable so that the settlement can grow rather than having to be completely rebuilt in case we want to expand. So in the first week, I designed the exterior habitat of my concept. And for the location, I selected the lunar South Pole because of its access to prolonged illumination as well as permanently shadowed craters. And some examples of the regions, as you can see, is like the Shoemaker or the Shackleton and others. This combination is valuable because sunlight can support power generation, while shadowed regions may contain water ice. The overall settlement uses a distributed modular architecture with interconnected habitat modules rather than a single structure. The concept is sized around 100 people with approximately 9,000 cubic meters of total space used in the construction, with an operational lifetime of 20 years. So this was my habitat concept, and it's a partially submerged concept so that there's easy access to the surface in case of an emergency or something like that. But before the settlement can become operational, we need systems capable of constructing and maintaining it. So in week 2, I focused on robotic assistance. And because the construction on the moon would be extremely difficult and dangerous for human beings, I incorporated autonomous robotic assistance. The first system I designed was an excavation bot designed to collect and transport lunar regolith. It uses a compact internal hopper and a swing-out suspension system that lowers the chassis for surface skimming. Rather than relying on complex digging arm designs like the normal ones we see of excavation, the design collects approximately 5 to 15 centimeters of regolith using angled doors to help reduce mechanical complexity and power, and how much it takes in power. So I also designed an universal modular manipulator, and it was a 7 degree of freedom robotic arm with interchangeable tools for tasks like gripping, welding, inspection, and drilling. So the tips of the robotic arm can be changed for different purposes at different times. And the idea was to use one modular platform for multiple maintenance tasks to separate, instead of getting a separate robot for each job. Once the infrastructure is established, the habitat also needs to support the people living there. So in terms of psychological help and aid, I included communal spaces which were designed to support social interactions and the well-being of the crews during long-duration missions. Then in week 4, I designed personal quarters alongside the communal areas, and because of the individual needs of the crew. The personal quarters would provide privacy, personalization, and a place to rest and decompress after a highly tedious activity. Food is another major part of the settlement, and it's one part that would make an extraterrestrial settlement sustainable. So the agricultural system was intended to reduce dependence on supplies from Earth whilst providing fresh and nutritious food. It also makes resource efficiency important because in a closed habitat, food production has to work within the wider resource system. Then, as we all know, healthcare becomes particularly important when the earth is no longer immediately accessible. So instead of designing one large medical dome, I propose a distributed medical system consisting of a central medical center and pods around the habitats for more accessible healthcare. This will provide advanced treatment and more essential and early time to detect sicknesses. The habitat also needs to extend beyond pressurized buildings. My transportation concepts connect the different parts of the habitat into with rovers and EVA to make the habitats accessible for different people at different places. I considered emergency response and EV operations, so mobility becomes part of the overall habitat infrastructure rather than an independent system. In week 8, I focused on habitat clothing and the division of labor. And I consider the astronaut or the crew members as part of the habitat system itself. So the clothing had to protect the crew whilst allowing mobility and comfort. So I explored both indoor and outdoor clothing concepts with environmental protection in mind. And this was my outdoor concept. And it's supposed to be built on the indoor concept. So people can wear the indoor clothes indoor, and when they have to go outside, they can just put something as simple as a helmet or something instead of having to change it to a completely different set of attire. Then finally, a habitat isn't really sustainable simply because of how the technology works. It needs people with different roles to operate it. So I divided the workforce into engineering and maintenance, science and research, life support and agriculture, as well as medicine and human services. And finally, governance. So all these people would be contributing to how well the habitats would operate. Ultimately, I approach this habitat as an integrated subsurface system and with a scalable modular architecture and a combination of robotics, life support, agriculture, and mobility to create the space or environments needed for long-term habitation. And beyond the moon, these systems can serve as a stepping stone towards deeper space exploration. For my vision of the moon, I think the moon is a proving ground for the technologies and systems we are designing that would eventually take us further into the solar system and even on Earth. Because one day I hope that we go beyond simply reaching the moon, and I hope we venture into places we've never seen or with places we've never reached or explored. I did a AI video of the overall concept, and I think, yeah. Can you please hear, if you can hear the sound, please tell me.
I'm not hearing any audio when you play it yet. Press play again.
Okay.
Okay.
Yeah.
Should be okay.
There it goes.
Your vitals look perfect, Commander.
That is good to hear, Doctor.
You are fit for another month.
Did you see the new Earth view?
Yes, it's absolutely stunning.
The habitat systems are performing perfectly.
Looking at these Earth memories keeps us grounded. Surface transportation connects the distributed lunar habitats. This allows people and resources to move safely between modules.
So this is the end of my presentation, and I'd like to say thank you to Dr. Jean and everyone I worked with throughout this presentation. I learned a lot.